So it's a pleasure to welcome you all to the 2026 Grubb Parsons lecture. For those who don't know, I'm Paul Chadwick, I'm the current head of the physics department. Good morning, you're very welcome. So for the history, Grubb Parsons was a telescope manufacturing company of great renown. The Grubb part is Thomas Grubb, who founded the company in Dublin in 1833, which became famous for excellent optical and telescope drive systems. It was eventually bought in 1925 by Thomas's son, Howard, by Sir Charles Parsons, hence the Parsons bit. He was inventor of the steam turbine and the youngest son of William Parsons, 3rd Earl of Ross, who was responsible for the Burr-Castle telescope, famously the largest telescope in existence at the time. The Grubb Parsons works were based at Heaton in Newcastle. They were of exceptional importance to the development of astronomy in the UK and around the world. Among the over 50 major telescopes they built are the Anglo-Australian telescope, the UK infrared telescope, and the William Herschel telescope. This was the last to be built by the company, which folded in 1985. The whole Parsons family had an interest in engineering, including Charles's wife, Catherine, and his daughter, Rachel. And I think Rachel deserves a shout-out. Rachel was one of the first women to study mechanical sciences at Cambridge. During the First World War, she was appointed the director of her father's firm, where she supervised the instruction of hundreds of women workers in the manufacture of steam turbines and other things necessary during the war. After the war, Rachel and Catherine Parsons and their supporters were infuriated by the introduction of the Restoration of Pre-War Practices Bill, which threatened to make it illegal for any engineering firm to employ women if they had not done so before the war. Opposition to the bill resulted in the formation of the Women's Engineering Society, with Rachel as the founding president in 1919. In that year, she also became one of the first 3 women to be admitted to the Royal Institution of Naval Architects, and a year later was one of the founders of Atalanta Limited, an all-female engineering company. Less than 10 years after the formation of the Women's Engineering Society, another pioneering and equally determined woman was born in Pennsylvania, Vera Rubin. Navigating what was at that time a male-dominated field, Rubin and her instrumentation expert colleague Kent Ford made the observations of galaxy rotation in the 1960s and 70s that ultimately provided convincing evidence for the existence of dark matter. The Vera C. Rubin telescope in Chile is named in her honour, and it is this telescope that will make the observations which today's speaker's work is based. Dr. Megan Schwamb is a graduate of the University of Pennsylvania and the California Institute of Technology. After holding a series of posts across the pond, she is now based at Queen's University in Belfast. Her research is focused on fundamental questions of how our solar system and others formed and evolved. She uses big data for planetary astronomy, particularly for studying the small body populations in the solar system, exploring seasonal processes on Mars, exoplanet detection, and citizen science projects in planetary science. She even has an asteroid, 11814 Schwamb, named after her. She is now co-chair of the Vera C. Rubin Legacy Survey of Space and Time Solar System Science Collaboration. I can tell you, it's quite hard to say. The exciting new era of solar system science that we ushered in by this survey is the subject of her talk today. Everyone please give a warm, warm welcome to the 2026 Grubb Parsons lecturer, Dr. Meg Schwamb. Meg.
Thank you so much. I've had such a good time so far visiting, and I'm so excited to tell you about what I don't know. But what I do know is that this facility behind me, which is the next generation, brand spanking new, ground-based observatory, is going to completely transform our view of the solar system. And so I got asked to give this talk. It was bittersweet because I went, but we're just about to start. But also, things are going to completely change the next 2 years. So I think it's kind of fun to show the enthusiasm, but also that astronomy and science is what we also don't know, right? We don't know all the answers right now. We tend to think that when we learn from textbooks because we learn fundamentals that have been around so long. But science is about how us studying the world around us and the universe around us change, right? And our knowledge changes. And so I realized that I'm really excited to give this talk because this observatory is hopefully weeks away from starting basically the largest movie of the night sky that it'll make for 10 years. But I want to sort of backtrack just a little bit because I'm a planetary astronomer, and so I wanted to sort of sell you on the fact why you should be Team Solar System and why you should care about the small bodies in the solar system and not worry about whether Pluto's a planet or not. It's not, but it's okay if you think it is. Justice for Ceres. Nobody cares about Ceres. It got demoted too. But the idea here being is that the small bodies I think of in the solar system, the asteroids, the comets, the Kuiper Belt objects, the Transneptunian objects, all these small bodies are the debris left over after planet formation. And by studying them, right, we get links into what happened, right? How did our solar system form and evolve? And that's sort of, I feel like, the warm and fuzzy like question, why are we here? We got to learn the history of the solar system, figure that partly out. And that exoplanets are amazing, right? Finding planets around other stars. But the best extrasolar planetary system we will ever study, at least in my lifetime, is this one we're in, right? Because we can study the small bodies, we can send missions to them, and there's history in there. I like to think of them as the relics, right, of leftover planet formation, and that I'm doing archaeology. Because by studying these and trying to disentangle how these objects have changed over the last 4.6 billion years, right? And then what stayed the same and what that tells us of how we built the planets. And then also how the solar system changed, because a lot of that history has been erased from the planets themselves. And so the small bodies, although they're tiny and they're test masses in a lot of ways, that when I model the solar system, I don't need to include them for gravity, but they reveal a lot of this hidden history we didn't know about. And this is going to change dramatically when these numbers increase with the Rubin Observatory. So I want to just give a little context for like what can we learn from studying these bodies, because obviously we can't send spacecraft to every one of them. ESA doesn't have a budget to do that. NASA doesn't either. But what we can do is use our remote techniques, either by taking each one of these little dots. So over here, we've got all the known asteroids. So each of these circles here are our terrestrial planets, right? So we're going from Mercury, Venus, Earth, Mars, and then out, we've got gas giant Jupiter. And so every dot here is a known asteroid, and its location currently in the sky from just a little while ago. I took this from a couple years ago. And so the point being is that this is so dense because we know of a lot of debris there. Much more than there are planets, right? And same thing in the outer solar system, although it's sparser. These are more icy bodies compared to the asteroids, which are more rocky. And so instead on this other side here, right, we've got the orbits of the giant planets. So we go from Jupiter, right, Jupiter inward, Saturn, Uranus, and Neptune. And so again, the structures within these objects, right, of these belts, the asteroid belt and the Kuiper belt, so the outer belt where Pluto is, these things tell us, right, about this hidden history. And so by studying these ensembles, how they compare to each other, how they're different, helps us understand what was the conditions in the planetesimal disk, right? The disk that was forming the cores of the giant planets, forming the terrestrial planets. And then also, how did the solar system then evolve after that? But also we get to understand some of the dynamics in the solar system too, and I'll talk a little bit about that. So one of the ways we do this is trying to get compositions. And so I'm showing some spectra where we're just splitting the light from these objects. I've got wavelength and just reflectance. So just looking at how much light is coming off of these objects in these different wavelengths, going from optical to near infrared. And so I'm really an outer solar system astronomer. I really don't care about the asteroids. I pretend to, even though I'm co-chair of a science collaboration where like half the people care about that. I really care about the icy stuff. It's cool. And so I'll show you more of the outer solar system examples just because it's closer to home. And so for us, most of these spectrum are flat or they have a little bit of signature water ice for most of the objects. But it means that if we can get broadband colors, right, instead, so we're taking an image and only getting some set of the light coming through. Here we've got going from green, G filter, R, I, Z, in the optical, right? We can get that slope that tells us a bunch about the composition or hints about the composition of these objects. And then these are the typical Kuiper objects, the majority of them that I will talk about how Rubin will discover them. but we also have a few large objects, the dwarf planets, Pluto. Pluto is a whole different beast compared to most of the objects in the outer solar system. It's the end stage of planet formation, the oligarchs, right before you get to forming cores of giant planets. So we have about 12 of those that we know of, and 9 to 12 of them. And they're typically round. And so they do have signatures of volatile ices like nitrogen ice or methane ice and CO2 and carbon dioxide. And so we see very different signatures in the near infrared and optical for those objects. So it's why Pluto went home. It fits much better with the rest of the Kuiper Belt large objects than it ever did, right, with the planets. And so from either getting spectra, being able to split the light out, that these objects reflect, the reflected sunlight back out, or by getting these broadband colors, especially for the fainter objects, we get these hints, right, of composition, or at least trying to put in classes of composition. We can also think about how these objects rotate, right? And so I'm going to use my phone because it's a good example, but the idea being is that, right, as these objects rotate, it's that area that you're seeing. And so more area, more light reflected back at you. And so the changes over time as these objects rotate, how they change in brightness, can tell us about shape. Right, so we're going from things that have changes due to being elliptical, or they're contact binaries, or just two objects that are basically kissing. We can see objects that are binaries that are close but influencing or moving in front of each other. And also for the very largest objects, we see albedo differences. So changes in the composition, changing how much light they're reflecting back. And so we can see spots in these objects. And so again, this is just from taking my telescope and pointing at these objects and counting up how many photons I get as this object rotates. And so we've already sort of learned, right, that there's such differences in composition, right, and shapes and sizes, right? And so these light curves are trying to get us inferences of what these objects look like. And I've just taken a smattering of small bodies. I haven't scaled them to the right size, but these are all things we've visited with spacecraft. And so part of the game here is to take the things I'm looking at remotely and try to tie it to what I can do when we can send a spacecraft and image it. For example, we didn't know the size of Pluto till New Horizons passed by because the atmosphere actually causes problems that from the ground we can't figure it out, or even from Hubble Space Telescope. So we need to send a spacecraft to actually image the surface to go, it ends here, this is where the atmosphere is. So, right, like it's now taking this and trying to link it back to everything we've learned. And so Pluto and Ceres, right, are our largest sort of objects of these small remnants of planet formation about. And then we have things like Arrokoth. So again, right, this is two objects stuck together. So again, telling us something about planet formation. And same things keep seeming to pop up. We see this is a short period comet, 67P, Cheremenko of Gerasimenko, and then asteroid Donald Johnson. And so we seem to be seeing that this sort of contact binary, two objects sort of just touching, seems to be coming up, especially among small objects. But we don't really know how many objects look like that, because we don't have rotations for most of the objects that have been discovered I showed you in those plots. But that's hopefully going to change soon. So I want to talk a little bit about the structure of the Kuiper Belt, and just to highlight the fact that I talked about physical properties, right? That we can glean something about composition by looking about how much light we reflect back in the object reflects back in different wavelengths, how we can get some proxy for shape, or composition in terms of if it's more round, by looking at how the light curve changes, how the light changes over time, we're getting reflected back. But the orbits themselves also help us out to do this. And so we can do this, right, by looking at their orbits. And so here, although it's cut off, I'll show you this is semi-major axis, so average distance from the sun versus elongation of the orbit, how elliptical it is, the eccentricity. And so I've put, for reference here, Neptune's out at 30 AU, and these are all, that was 4,000, 5,000 Kuiper objects we know of. Pluto's sitting in here, in what's known as the 3-2 mean motion resonance. It goes around twice every time Neptune goes around 3 times. And so the point is, right, that all of the structure is really complicated, but it's all understood by understanding Neptune's past movements. And so I can show this view slightly differently here, showing inclination, so how inclined the orbit is to the planet and solar system versus that semi-major axis. And so the same thing sort of emerges, but there's also this really sort of low inclination, low eccentricity population that we call the co-classicals. And so we think part of the Kuiper belt formed in place, and that those co-classicals are the primordial objects. Arakoth is one of them that we think formed there. It's telling us about planet formation out at 48. And AU is the average distance between the Earth and the Sun, versus stuff like Pluto that came from more inward. It has more excited orbits, higher inclination, higher eccentricities. And so the punchline I want to give away, right, is that we know that the giant planets have moved around because of studying the orbits of the Kuiper belt and the asteroid belt. And so to get all of that complex structure, I could just give you a whole hour-long talk on just that, but I figure I will bore you. But I could, because there's so much in each one of those orbits, even though these objects are test masses, right? It's like scattering marbles and throwing a basketball at it, right? They're just going to go everywhere, right? But we can actually reconstruct partly what happened. And so based on particularly Pluto's orbit and those objects that are highly inclined and highly eccentric that are locked into this mean motion resonance dance with Neptune, we know that Neptune had to migrate about 10 astronomical units. And that the best way to make this happen is that Jupiter moved inward, and then Saturn, Uranus, and Neptune moved outward, scattering planetesimals that were in the outer part of the solar system. And then stopped at where the co-classicals were, because the density was lower. And that this is the event that formed the Oort cloud, our source of long-period comets. And so this is the hidden history. You don't get any information basically from the giant planets themselves. You really, the way we figured this out is really from looking at how you can reproduce these orbits that we see today, because if everything formed in this beautiful thin disk, right, of material, why would we have things on such eccentric orbits and inclined orbits if there is gas around the disk? That would circularize any object. So the minute the gas went away, something had to happen gravitationally to scatter objects like Pluto into the outer solar system. So I want to show you this animation, this numerical model by David Nisforny that goes through that. And so you'll see a third ice giant, a second Neptune, just got ejected from the solar system. And that, if you notice really quickly, and we'll go back over it, that the planets went very eccentric very quickly. And so the thought is that over time, Jupiter and Saturn were scattering planetesimals, but it got too much and they actually became eccentric, and then started significantly scattering objects, influencing the other ice giants, Uranus and Neptune, and the other ice giant. And so that interaction is basically transfer of angular momentum. I like to think of it as take a basketball, right, and a BB gun. If you shoot enough BBs at it, you can make that basketball fly. Even though the mass difference is huge, you can do enough for them fast enough, you can make that basketball move. And it's the same thing here. Jupiter scattered most things outward because it's so big and massive. I'm going to use a baseball analogy. I know it's the American in me coming out, but the idea is that, right, Jupiter hits home runs and kicks stuff out of the park. So it, right, kicks things out of our solar system, right, and so it moves inward. And Uranus, Neptune, and Saturn tend to move things inward more than they do outward, and so they, right, move outward. And then the poor extra Neptune, it interacted with Saturn and got kicked out of the solar system to never be seen again. And the only signature of this object is from the orbits of the Kuiper belt objects and the ratios of those different populations. So the best fit comes from this sort of model. And so that's taking that simulation and just stretching it out over time, showing you the semi-major axis of these objects. And so the colors are the different objects, and so the lines are just showing the closest and furthest points of the orbit. And so there's the poor ice giant that got kicked out, interacted with Saturn, and just went straight out. And so here's Neptune moving, right? And so you can just see there's a very abrupt jump, and it moves out to 30 AU, and same thing, Uranus takes a big jump to movement too. And so this reproduces our best view orbits and structure of the Kuiper belt we know of today. So this is why I think it's important to study these small bodies, because we're really doing the archaeology on the hidden history of the solar system that we don't see from studying the planets. But also these objects are active too. Many of them are, not all of them, but I just want to highlight that they're not all dead worlds. That some of them are active, some of them are fuzzy comets, and so this is just showing you an image from a half-meter telescope. This is Echolus, so it's a short period comet / middle solar system object, and so comets have coma. They look fuzzy compared to the stars, and this is a Hubble Space Telescope image of an active asteroid, a comet in the asteroid belt. And so we see those classic tails. The comet on the Hubble space images has multiple tails. The story that everyone likes to say is comets are like cats. They're unpredictable. We don't fully understand them. We have some sense, but they do what they want. And so every comet seems to behave slightly differently. And so with the picture we've been trying to put together is how does all of this go together? So the active objects, right, aren't just a separate thing, right? They come from these other populations, right? So, right, our centaurs are middle solar system objects, which are one flavor of comets. They are escapees from the Kuiper Belt. They're like Pluto, smaller, but they're escapees from the dynamics from the giant planets. And they're hitting through the pinball machine, going towards, right, that of the giant planets, and then eventually most get kicked out, but some become short period comets, like 67P. And so again, right, there's these connections between these different populations. We also know the asteroid belt is active too. We see comets or objects acting like comets in the asteroid belt. So we have our long period comets that come from the Oort cloud, which is the same, they originate from the same population most of the Kuiper belt did, but they just got scattered further out and occasionally get knocked in by passing stars. And so all of these objects are telling us some other side of like the coin, right, of planet formation, because understanding how these objects are active tells us what's inside of them too. So if we can study the mechanisms that's causing this activity, right, we also get another way to peer into their interiors. And that again leads us back to that original planetesimal disk. And I'd be remiss if I didn't say anything about interstellar objects, because we've had like one that was discovered last year. Interstellar objects are planetesimals that formed around other solar systems and then clearly got kicked out. And guess what? That's what Jupiter did to a whole bunch of other planetesimals. So I like to think of it as a toddler with a biscuit, right? If you ever give them a toddler a biscuit and then look out of the ground below, there's all those crumbs, right? And so the same thing here, right? By the giant planets in those systems moving about and kicking out planetesimals, they're running around in the galaxy, right? In the Milky Way, just wandering. And so interstellar objects are those planetesimals from other solar systems that got kicked out, that then feel the gravitational well of the sun and come in. But they're moving too fast to stop, right, or become bound. And so they're on hyperbolic orbits that get kinked as they go around the sun. And so everything that I talked about, how I study small bodies in the solar system, you can deploy on interstellar objects. And so we know of 3 of these objects now. You don't have a long time to follow them because they're moving so fast, but you can deploy the same things. And so now we have this brand new window into planet formation. We don't have to go and sample it from some other solar system, which we're not going to be able to send a probe to anytime soon. I just got to wait for them to come to us and for us to discover them. So I wanted to sort of give you the 2 sides, that like when we're doing small body science and solar system, we're also occasionally doing objects that aren't from our home at all. And so this is just showing you the orbit for Comet 2I Borisov from a couple years ago. And in this case, it was active like a comet. But it looked very similar to solar system comets. The current interstellar object that people are studying, 3I Atlas, looks very different and probably came from a very old star within the galaxy. And so we now get to sort of do comparative planetology on a small body level, not just for the exoplanet people anymore. And this is a really exciting field. And I'll talk a little bit more about that, thinking about Rubin Observatory. So I want to just take a second to talk about how do we find moving objects. And so again, asteroids are wanderers, right? Planets are wanderers, right? We're looking for the objects that are moving in the images. And so it's either taking a bunch of images on a night and looking for what stays stationary, all the circles in this image, and then coming back to the same spot another night and just finding all the things that are the same and looking for what changed. Or taking a bunch of observations on a single night and looking for what moved. And so Eris, the most massive dwarf planet in the outer solar system, is sitting right here. And that object that just blips in and out, that's an asteroid. And so by how fast they're moving, particularly we look typically opposite, to the Earth's motion. So we're using the parallax by using the Earth's velocity to help us. So we look perpendicular to the Earth's motion. And that helps us get an estimate for distance. By seeing how fast these objects are moving on sky, since it's mostly the Earth's motion, we can actually get an idea of distance, just like using the parallax effect. And so that's how we did things. It all kind of changes in the next couple of weeks with the Rubin Observatory. And so the Rubin Observatory is this next generation facility. It's going to execute the Legacy Survey of Space and Time, the LSST. And so the start date should hopefully, fingers crossed, be in a couple weeks. And so this telescope is being built in Chile. It's basically done. They're doing the final bits of commissioning to get the optics as perfect as they can get. And so this telescope is sitting on Cerro Pachón. It's been over a decade trying to build this sucker. But it is going to be revolutionary because it's the fastest scanner of this night sky. So we're combining a big, huge field of view on a telescope, 45 times the field of view of the full moon, in a single image. Speed, this is the fastest telescope anyone's ever built. Plus a big aperture. We have a big light bucket. So huge 8.2 mirror. That's basically a primary and tertiary mirror combined, so you can get this big wide field of view and focus. And it's able to survey the night sky, basically the entire visible night sky from Chile every 3 nights. So technically this is a wonder to do. And so if you can combine these all three, you can do a whole bunch of really cool, interesting science on everything from the very small, thinking about our solar system going all the way out to thinking about the very big cosmology and dark energy and the expansion of the universe. So this is done in a really interesting way. It's done by having this mirror that is a combination of being a primary mirror. So effectively, instead of being 8 meter, we're 6 meter here, where this tertiary helps you basically get this huge field of view and focus. So that's the big challenge, is that you can get big fields of view, but you get blurry images. So this design, by combining the two mirrors together, so the light hits the primary on the outside, goes out to the secondary, to the tertiary in the middle, and then up to the camera that's heavy and literally sitting on prime focus above that mirror. And so everything's in focus, and you're off to the races if you can strap on the biggest camera ever onto this top of this telescope, which is what they've done. So the LSST camera is the biggest pixel camera ever built, has the same technology that's in our phones, deployed with 3,200 megapixels. Just humans for scale, but this camera's huge. I'll show you a picture on the summit. But just to show you image quality, that is in the lab with Romesco broccoli. I love the fact the engineer brought it in to test things are working and then ate that for dinner. The other thing is this camera has the ability to put in 6 filters or swap in different optical filters. So we get 6 filters of the sky, basically getting the images of the sky in these 6 different wavelengths that go from optical into a little bit into the ultraviolet and a little bit into the infrared. And so to achieve all this, you need the fastest telescope in the world. So this is the Simonier telescope in the Rubin Observatory dome. If you were in there and tried to run from it, it will hit you, because it has to be that fast to be able to go and survey the sky, by moving quickly so that it can take an image and quickly move, and also go all the way down, because the filters are so heavy, down to the filter exchange box and back out. Usually your filters are on your camera. You can't do this with this big field of view. So they have to actually make this telescope fast so it can go all the way from one side of the dome to the other. So I would definitely not want to be in there when it's moving. It will hit you. I think the fastest human still can't beat it. So the camera, this is just to give you the size. This is it coming to the summit. It was delivered in May 2024, and then they've been commissioning it since April last year. And so the telescope is on sky, and it has been taking data and taking commissioning data. And so it is now here. Instead of all these talks where I'm like, it's coming eventually, this thing is primed and almost ready to go. And I want to just give you some sense of scale here of how much data on sky I can take, particularly for the astronomers in the room that aren't as familiar with Rubin. This is a simulated simulation from using the Rubin scheduler, assuming weather conditions from Gemini South Observatory. Each color is using one of the different filters. And I just want to show you that this is ridiculously fast. This is so much sky coverage, right? Because in every 3 nights, you can cover the whole entire southern visible sky from Chile. And so this is what makes it unprecedented, right? The depth, you can go to about 25th magnitude an hour, 4.5 roughly, 25th, right? And so we're getting depth and sky coverage. We often get one or the other. Plus the fact that we can cover so much sky, right? So quickly and efficiently. This thing has been built to survey. And so just summing up all the visits it will do over the sky, it's going to roughly do about 800, 900 visits in what's called the wide, fast, deep, the sort of green bit. So the real trick here is that the legacy survey space and time is a misnomer because it's actually a whole bunch of surveys stuck together, including getting the northern part of the ecliptic plane, northern part of the solar system, because getting half of it is kind of bad, because then if there's odd things about distributions of objects, I miss it. So thanks, everybody, for getting us the northern part of the sky, too, where we can get the other half of the solar system for objects that won't move over 10 years. But the idea here is that we have 10 years of observations, right? Not just 1 year of discovery, 10 years of observations from the LSST. So it gets you all these big things, right? It gets you the ability to probe dark matter and dark energy, inventory the solar system, map the Milky Way, and explore the transient optical sky. So these are the 4 science drivers. Solar system is one of them. We're also the trash for transients, so everyone who loves supernovae or lensing events, you really don't want the asteroids crossing over your fields or your fancy supernovae and then contaminating it, and so it looks cool and it's not. There's so many millions of asteroids that actually Rubin needed to have solar system be a theme to make sure we were moving them quickly for everybody else. But their trash is my treasure, so I'm happy with it. And so I want to just highlight that this is big data and scary. Glad I got a laugh. I was like, am I at a generation where people don't know this? But the point being, for solar system, it is for us. Although it's tiny, I could download it, but onto a desktop computer, it's still big in terms of the numbers, and I'll talk about it in a second. And that we're getting hundreds of observations of solar system objects in these different filters over 10 years. More so that the plot I did of the Kuiper Belt, I did as a scatter plot. You can't do that with what we expect from LSST. But I want to highlight that, like, this is because this is so much data. There's millions of transient objects, including moving objects, that will be found each night. We need new ways of working together to figure this out. And so there's actually 8 science collaborations. I co-lead the solar system science collaboration, but there's all of these different science collaborations that have been around since 2008 trying to get ready for this telescope and get ready to go for Rubin data. And so preparing for this has been a challenge for us as a community, because this is so much data that we have to go to the computers where the data is to work with it. And that for solar system, we have to have one pipeline that's finding most moving objects, because we can't have 100 astronomers running their own on the data. It's just too big. And so I think it's kind of fitting that this telescope is named after Vera Rubin, because of the fact that, one, she championed, everyone being included to do science, particularly given her, interactions in science. I didn't know, as a graduate student at Caltech, that she's the reason I could observe at Palomar Observatory. Right, here's the 200-inch. It was my first telescope I was ever on, and I didn't know that she was not allowed to observe there initially because there was no women's toilet. And she fixed that by cutting out a triangle, pasting it on the door, the little man, and said, "There, I fixed it." Right, and then she got to observe there. And so as a graduate student, I never knew that had happened. That I could observe there because she argued the point, right, very succinctly, that this wasn't an issue, right? She should be there like everybody else. And so I think it's fitting because of her contributions for understanding that there's dark matter, right, in our galaxies and in the universe, right? This hidden, unseen matter that is changing how stars are rotating, right, around the galaxies, the centers of their galaxies. That, she's been instrumental in that, but also, right, the fact that everyone has to work together, right? I think, again, that collaborative spirit and many things she did later in her career for increasing diversity and inclusion within astronomy. And so, it's exciting that Rubin's nearly online, and that for us, because there's so much data, right, coming in, it's 15 to 20 terabytes of image and catalog data a night. We need a solar system pipeline run at the observatory, running nightly, to find objects. And so it's going to work in one way by every time there's an image, every 60 seconds after the image is read out, it'll try to identify known solar system objects we've already know about and alert that those exist. And then during the day, it'll sift through all the transient objects, looking for new solar system objects and trying to link individual transient detections together and place those on heliocentric orbits. And so, luckily for us, this is all doable now. And so the Rubin solar system pipelines are working. This is the release of the images from the first look observations released last June. And this is just a snapshot of the new solar system objects, mainly asteroids that were discovered in these 2 Rubin pointings. Only 2. That they took a bunch of observations at. So this is just a taster, but for me, this was just relief and excitement. So the blue, the cyan are asteroids, the magenta are, I believe, outer solar system objects, and the purple, I think, are near-Earth asteroids. And so most of these are main belt asteroids, and so those 2 pointings, right, show that this pipeline that's being developed for over a decade works. And so when this thing fully turns online, solar system objects are really coming out at full speed. Because there's so much challenge and because there's so much data that new algorithms had to be developed, but they're ready to go. And that's the exciting bit for me. But what I want to tell you about for my last bit of this talk is what science are we going to do with Rubin Observatory? And to do that, we actually had to build a survey simulator, because for me to tell you how many solar system objects we discovered and how and when that's going to happen, we actually have to do a lot of calculations, because this is so many objects. There was no software that could do this and hold up to the amount of computation. So my team built SORCA, which is a survey simulator for solar system objects built for Rubin Observatory, but can be used for other observatories. It's a whole team that's worked for 7 years to make this happen. And so the animation is really cool, but I also want to highlight that a lot of work went into getting that animation. And so why do I care about a solar survey simulator? Why do I need to write code to figure out what I think Rubin Observatory might find? I just want to highlight the science here for a second to say, it's not just about predicting the numbers. Once Rubin starts finding these objects, right, I can take what we found and didn't find and use that information to figure out what the actual populations of these small bodies look like. Right, because I can take an input population for the orbits and their physical properties and run that through SORCA, and I get the right model box of detections from Rubin Observatory. And then I can compare that to what was actually found in terms of their colors, their sizes, the numbers, their locations on the sky, and then tune my model and keep going until I get something that statistically matches what we see in our observations. So I'm going to show you the predictions, but this SORCA is really powerful for doing these multiple things. And I want to highlight just that it's tricky to do this, because we have to take count where the telescope pointed, whether or not the object lands within the pointing, and if it hit into a detector gap. There's actually tiny gaps within detectors that solar system objects can land in. They have to be bright enough in the specific filter. As I showed you, they are vary in the different filters, right, depending on their brightness. So we have to worry about that. We have to worry about their detection efficiency. We have to worry about other effects of the optics, and also how the processing software gets there. And so by adding in, right, the properties of the small body population as well, the sizes, their orbits, their colors, how their brightness changes, we can then add that together in SORCA, and it will do all the calculations, right, to show you that. And I'll just highlight, it's figuring out where these objects are in the sky, ephemeris generation, right, whether that's in the field of view, calculating how bright it is. So doing this, including the fact that these objects are moving in distance, possibly have cometary activity that changes their brightness, has rotational effects. Right, how things are detected, right? There's detection efficiencies depending on how bright the apparent magnitude of these objects are. Adding in the footprint, so now figuring out we've gotten almost all the way through, are you in one of those detector gaps? And then actually applying how the pipeline is finding those moving objects, because it's not going to just take one detection, it's going to take multiple detections and try to link those together. And it has efficiencies for how well it can do that depending on the velocity of the object. So if you do all that and you get it right, you can bake this into the simulation. And so this is what we will find with LSST. Every flash here is a solar system object detected. And so they become darker after they've been found. Some of these will be new discoveries, some of them won't. And so the blue are the Kuiper Belt objects, the yellow are the main belt asteroids, the pink are the Jupiter Trojans. They're locked in that mean motion resonance trailing and leading Jupiter, but they're really part of the asteroid belt. And those red are the potentially hazardous and near-Earth asteroids. And so you already see that we're now about 2.4 years in, and that flashing's already getting less. So something we didn't quite appreciate was that we're going to find these objects right early on in the survey. Should probably have known that, but we didn't actually. And no one had been really thinking about that much in the community. We didn't really know how early. But notice, it's still flashing and we're already 3.5, 4 years in. And so you notice for all the objects that are there, we're now 4.6 million objects discovered or observed, we're going to get all those hundreds of measurements of them too. So we're going to get photometry and different filters, right? Measure their brightness over the 10 years. The bonus is we get them right up front. We get them the first few years. So while people care about cosmology and how the universe expands, good luck, you've got 10 years to figure that out. I get a lot of stuff next year. So it's like, buckle up, because there's no vacation the next 2 years, because all of this stuff is going to come in. And I want to highlight, when you get this sheer number of objects, you get the weirdos, you get the rare gems, you get the things we didn't see in the previous our view of the solar system, because we didn't have the numbers, right? So when you have a step change in number of objects, and I'll give you a context in a second, that's when you start finding the rare stuff that tests whether we understand how Neptune migrated. And that's the exciting bit, is that we can see how this plays out with Sorka, and that I can now compare this to what we actually find from Rubin, and see if we're even right on the right path over the first few years. So we're still going, and there's still little flashes. And again, right, we're still finding some objects, because as we observe the sky more often, the smaller objects will become detectable, just because there's more chances to see them if they're bright enough. And also some objects are moving inward, and so that helps, right, as they reflect more sunlight from the sun, right, as they move inward. So now we're at 10 years, about 5.4 million solar system objects will be observed. Okay, so how's that compare to discovery? So it's 89,000 new near-Earth asteroids. Good, because I don't want anything to hit the Earth. I imagine nobody else does. About 3.7 million new main belt asteroids. 1,200 new centaurs, these middle solar system objects, escapees from the Kuiper Belt, and about 32,000 new trans-Neptunian objects or Kuiper objects. Okay, so what does that actually mean in terms of relative numbers? It's about 2.3 times the number of near-Earth objects that have been found by all humans to date. Everybody who's ever found a near-Earth asteroid, we're going to find 2.3 times those with Rubin. Everything we've found to date, we're getting 2.3 times that in the next few years. About 2.7 times the number of main belt asteroids that we know of today, so roughly a factor of 3. It's about 7 to 12 times more, so about an order of magnitude more centaurs than we know of. It's about 6 times the number of Kuiper objects. So we get way out of that scatter plot, I'm going to have to do something else. So we're going to have new techniques for analyzing this data, right? And just the sheer numbers that come in early. And then most of these objects are going to have color. So just to give you some sense here, this is showing mainly work from Jake Herlander, a grad student at University of Washington, that for looking at, these are all, the near-Earth asteroids, main belt asteroids, the Jupiter Trojans, and the trans-Neptunian objects or Kuiper objects. The average number of observations is about several hundred. Split in these different filters. Many of them, especially the outer solar system, get 9 years, 10 years of observations. Right, same thing for the main belt asteroids. near-Earth objects are moving pretty fast. We only get about 3 months. But it means we get colors for huge fractions of these, right? Way more than we have today, for free. I don't have to go try to apply for telescope time. It's going to come out from this. Right. And just to emphasize, right, like these things are coming soon. This is just showing the centaurs for different definitions of the population. And basically here, right, we're getting about 60%, 70% of the population in the first 3 years. But a better way to show this is this plot. Right? Because this is Jake Kurlander's paper of taking all the like asteroids, the Trans-Neptunian objects, Kuiper objects, the potentially hazardous asteroids, and plotting their locations on sky. Doing for every year. This is 0 to 2. That's everybody. That's every other year combined. I don't know how to deal with that yet. Like, I'm still getting used to that realization. Like, it's all coming now, right? This thing turns on, and it's a fire hose that's coming at us. And so the weird and the wonderful are going to be in there, right? And we'll be able to see it. So I just want to highlight a couple of things we're going to get out that are going to be cool from the survey, beyond just, oh my God, so many more objects, what the hell do I do with that? One is that Comet Interceptor, the ESA mission that has been designed and led by UK, was proposed by UK researchers. It's going to be basically a spacecraft that splits into 3 that is going to observe a brand new comet coming into our solar system from the Oort cloud to explore how these objects evolve when they come freshly in from the really distant solar system. This is a bonkers mission. I mean, they don't know where the hell they're going. I don't know how ESA let this through. Like, literally, they don't know where they're going. Guess who's going to find their target? Rubin. Yeah, they're going to park where JWST is out at L2, the second Lagrange point from the Earth and the Sun. They're going to park there and wait for Rubin to find their target that fits within their orbital parameters and then go there. So, like, this is incredible that, like, this facility enables this kind of crazy mission to be greenlit by ESA, right? To study a comet in 3 dimensions. We don't understand activity in the asteroid belt. We see there's some correlation with the orbit of Jupiter. We don't fully understand why. It's a really tiny sample. We're going to find like 3 times the number of main belt asteroids. These things are going to be monitored for 10 years with hundreds of observations. If they become comets, we're going to see it. For free. I don't have to do anything. And so this is the exciting bit, is we don't just get to study them, and we don't have to struggle anymore to get follow-up. We now need to do other follow-up observations. But we're going to get whether these objects are acting like comets for free as the survey keeps going. Because we'll know where these objects are already. And so they'll be in the alert stream being sent out as they get imaged. We don't have to wait for them to be linked after the first few years. What about interstellar objects? Well, good news and bad news. Rosemary Dorsey, who's a postdoc at the University of Finland, and also was a graduate student in New Zealand at University of Christchurch, she modeled non-active interstellar objects, so ones that didn't have a very strong coma, and found it's about 6 to 51 objects over the 10 years of the LSST. Possibly. Big, error bars there. But that third interstellar object landed in the middle of the Rubin science validation field. And so that little star that's moving in the image, that is the 3A Atlas, basically the positional arc in the nominal Rubin Science Validation Survey. So this survey is to shake down the observatory system and the data management pipelines that had to be built over a decade because this thing is so complex. And 3A Atlas was just luckily landed in there. And so they actually observed 3A Atlas several days before it was discovered, but they weren't running the solar system pipelines. And so they already bagged one effectively, and they actually can see in these observations that the object changed. It's much more fuzzy here than it was over here. It's there. So we saw evolution for this new interstellar object, seeing its sublimation of ices change, right, over those initial days with Rubin. So now that whole estimate of like 5 to 61 might be much higher because they already bagged one if they were actually running, which I think is exciting. And so this is a whole new area that's going to be opened up. So either we're going to find lots or we're going to have to wait till year 9 to maybe see one. We have no idea. I just want to highlight that also the inner solar system is still weird. We know of one object that is has orbit inward of Venus, Axolotl. We, as a solar system community, petitioned Rubin to change their observing cadence because they were not observing close to the sun. Big glass pointed at a really hot luminous object. Not what anyone wants to do, but they're going to observe near twilight, so very close to the sun. This is solar elongation, so how close to the sun you're observing, and the number of visits. And so the blue was original baseline. They weren't going to observe anywhere near it, and we petitioned that they should take some time in the twilight when the sun is setting and rising to look there to find these objects, because Rubin Observatory is basically the only beast that can look for this stuff. We know of one. We have no idea why it's there. It wasn't predicted to be there. So we have no idea how big this population is. So I think this is a completely new area of the solar system we're going to get answers for when Rubin starts fully observing. And I'd be remiss to not talk about Planet 9, because someone's going to ask me, right? Planet 9 has been proposed because very distant solar system objects look to be in aligned orbits. If Planet 9 is there, I don't think it is, but I want to be proven wrong. Rubin can see it. So the prediction from Bagatine and Brown for Planet 9 is that the nominal orbit is that it's sitting somewhere in the northern part of the ecliptic, which we are going to look at. And so this is just showing the sky coverage within Rubin, and then showing the sort of predicted magnitudes. And so in this area where it's likely is, it's well above the flux limit. So if it's there, it should be screaming in those images. If it's not there, we're going to find hundreds of objects that should be perturbed by it, and then check whether it's there or not. So I can't answer whether there's Planet 9 or how many planets are in the solar system, but literally in 3 years, we're going to be able to answer that question, whether Planet 9 exists or not. And the last thing I just want to raise is that if you're interested in aliens, call it technosignatures. We're going to do the best technosignature search in the solar system because we get colors. So we get these broadband compositions, and guess what looks really weird in the solar system? Elon Musk's Tesla. That red Tesla is annoying, but it looks really different than the asteroids. And so if there's just some hunk of metal, spacecraft hanging out, that's not ours, we'll know. I mean, to limits. But that's, I think, the exciting thing is that Rubin will be able to tell us the answer to that as well. So, and I just want to highlight that we brought everyone together in the Solar System Science Collaboration the past few days, last month, to start working with this Rubin data. And so we have the first data. We have 94,000 asteroids that were discovered in the Science Validation Survey because they had to send the data to the Minor Planet Center, the clearinghouse for identifying and cataloging moving objects, which is great for us because that data is public. And so these are the first plots using Rubin data. Now it's not the, 3 million new objects, but this is just the taster survey, right? This is the teaser to get the telescope going. We're going to be finding so many more objects. And so that's the exciting bit, is that we're going through this data now, right, looking for objects and studying them. And so with that, I will leave the simulation showing the number of objects on sky in the first year, because I think it shows how everything's going to change when Rubin finally fully turns online. And how hopefully I've explained to you, maybe the excitement's come through, that everything is going to change. We're going to rewrite the textbooks. And I don't fully know what the answers are going to be, but I bet people in this room are going to be the ones, especially the undergraduate students and the graduate students, who might eventually be answering those questions. Whether it's with solar system data or any of the other Rubin data. Because it's just this amazing facility. And so it's a really great time to be doing astronomy, particularly with this facility coming online. So with that, I'll take any questions.
Bear with me. So this one's. So, sure there are a lot of questions stimulated by that. So very, very tough. Do I see any hands? Dave.
Thank you, Megan. That was a very nice talk. So, with any new mission, of course, there's always surprises in terms of what you might find. What do you think might be the greatest discovery made for like solar system science from LSST?
The thing we didn't expect, right? Like, that's always the thing, right? Like, when we expect things, right, it's great. You know, tick box, we knew stuff. But every mission, every spacecraft we've ever sent, right, we're seeing this with JWST, right? There finds the stuff that we didn't expect. And so I'm excited for what I didn't put on this list. And so just an example of that, I didn't want to go too much into it, for time, was that this is a plot of an asteroid from that first look data, because it was taking so many shots, which is not what the cadence will be. You can see the variation from the rotational light curve. So here is different filters. It's not the same object, but an object similar. And it's going up and down because that's the rotational light curve. And you're seeing composition by seeing the different bands. And so this is the fastest asteroid in the main belt, rotator in the main belt asteroid. And that means that it's really tiny, which shouldn't be that case. The thought is that these things are rubble piles, so this thing should have blown apart. So already this thing from the first look data is that we have monoliths, we have like hunks of just solid rock on the small end sitting in the asteroid belt. So that's just one example of we didn't predict that. And that's just in the first look data.
Sorry, quite revolutionary.
Yeah.
Thanks very much. So I'm an engineer by background, so I probably shouldn't be in the room, but anyway. A lot of engineering now, we're using AI really well to look through data sets to be able to predict compositions and things that work. I just wondered if you could talk a bit about how you expect AI to become more prevalent, or whether you think that computation models that you've got that exist already will be the data processing. Because, you know, you talked about the fact that you've got big data here. AI is really good at big data.
Yeah, that's a great question. So AI is going to be a whole component. One thing that's happening now is to finish these solar system pipelines and other pipelines. One is just the AI coding, that the step change in the last 6 months that I know Rubin commissioning people are using these things to help build these quick tools they need that they didn't have, right? Because they're not quite online to do things. And so one, just in that era of like how fast people are able to learn and launch code, right, has changed. And I think that is going to be one thing that we're all going to be using in some sense. Particularly because the way that these LLM algorithms learn, software is really easy. There's rules, right? And so translating old code and porting it over to a new language, like going from Fortran to Python, these things are pretty good at getting you 90% of the way there. But also, right, it is so much data to sift through. And so, yes, particularly for the oddballs, there's looking at using different types of machine learning algorithms to pick them out. And so one group doing that in the UK is run by Chris Lintott and the University of Oxford. And they're basically taking these Gaussian models and neural nets to basically predict this is what the solar system looks like, then find me everything that's different. So we'll be doing a combination of all of that, I think, of using, right, helping to write the code we need in terms of analysis. Also these sifting algorithms to find those odd objects. When you have, 5 million asteroids, yeah, you're going to need something to be able to pick out the things that are outliers. So also machine learning is being used to already deployed in the system to figure out what's real or quote bogus. There's a lot of things in detector defects and things like that. And so even in the discovery algorithms, they're running these machine learning algorithms that have been trained up to identify things that are artifacts from the image subtraction to look for moving objects and other transients. So it's being deployed now and being used, right? But I think it's all going to be a huge component, particularly looking for how we find the needle in the haystack. So obviously for astrophysics, transients and supernovae, they have millions of detections a night, right? They have to do that on a much higher scale. solar system were behind on this. And so we're starting to learn from what people have been doing in the rest of astrophysics. So yeah, it's going to be a huge component. And how that interplays, I think, is going to be interesting as we go. But that's one of the things I'm doing next week is bringing a collaborator that's more an expert in machine learning to be like, cool, what do we do now? Help me learn how to use these tools. So definitely will be a part of it.
False.
Do I wait for the microphone or just shout?
That's right there.
I'm good at shouting. Yeah, so you mentioned Elon Musk. So what
Right, okay.
you talked about the effect of Starlink? Not so much Starlink. I think Starlink is small fry compared to the, was it hundreds of thousands of new satellites that are being planned to be launched, that they will leave streaks
Yes.
on your
There's been a
on
lot.
your images.
Yeah.
Particularly for my science and work on cosmology, maybe not that big a deal. But for you, the streaks must be quite a problem.
So we all thought that.
Yeah.
We sold that. Don't tell the Rubin people, but to argue for the Twilight survey, they only were going to pick one or two of these surveys to tack on to the rest of this cadence. And we went, we're worried about satellites because particularly at twilight, they're brighter because they're glinted, there's more glints, right, from as they're changing position and stuff like that. So we sold it on that. Some simulations now show that it's probably not going to be as big of an issue, but nobody knows because we don't know how much stuff is going up. I mean, now they want AI data centers in space, so like it might still be a problem. But we actually did advocate that, like, since nobody knew, we're like, this like twilight space you can only get with Rubin. Do it early because we have no idea what the hell is going on with satellites, and like no one's really regulating it, right? So yeah, that's one reason. A lot of, at least in the main survey, losing a little bit of a really big thing is still a lot, and so it's not a huge issue, mainly because there's still a lot of pixels, and because they're often tumbling, right, or they're moving, right, we see it's different than a solar system object because they're moving so fast, it's a solid streak. The algorithms, like the real bogus, are trying to pull those out, right, before it gets down further in the stream. So right now, there's not a huge issue with the satellites, but we still don't like them.
The numbers projected to increase by
Yeah.
a factor of 10 or 100.
Will it actually all happen? I don't know. But yeah, so, but right now, Rubin should be okay, and at least they're now, everyone seems to be talking more as we raise this issue. So yeah, it's a concern, but right now we still think we can get good data.
Chris?
Thank you. How well are you going to be able to reconstruct the planetary migration event? What's your best guess for how tightly you can constrain that?
No one knows. So interestingly, when we were trying to argue about the Rubin cadence, because the cadence was roughly sort of specified by the specs of getting the core science areas, but there's about 10% of time that can be tweaked. And so when we had to do this and come up with metrics for what's bad for solar system science, nobody could give me, like, to understand how Neptune moved this way, I need 10,000 or 100,000 Kuiper objects. So I know no one ever came up with a number. So I think it's very hard to tell because all of these models for how the solar system is migrated, all are reactive. They come from, here's the data and we need to explain that, and then they go back and they go, what happens if we do this? So I don't actually know. I think that given we already have we have a third ice giant thrown in there, we already have a lot of the detail. Like we have the broad strokes of that painting and we know a lot about it. We're now getting into fine detail. So I think it's going to matter about the color distribution, this weird stuff that we didn't expect to be in the outer solar system. That's going to be particular on that side. I think there's still a little bit of debate over whether Saturn and Jupiter moved inward due to gas migration, like exoplanets have. They're tightly close to a star and then moved back out, which could have basically messed up the asteroid belt, mixed it, and then cut off Mars from its feeding zone because Mars is weirdly small compared to where it should be. That some people still debate. They call it the grand tack because you have to like turn back around. I love the analogies for these models. The other one is the Nice model because they were drinking wine in Nice when they came up with it at the observatory. Yeah, gotta love planetary astronomers. So whether grand tack is real, I think we'll get more insight into, but no one's given me I need this many objects with this many colors to give me this answer. So it's part of the love and hate of these models is that like they can explain when you know. It doesn't have anything that's super predictive that you go, that we didn't see, and there it is right before, but now it's there. So don't know. the dynamicists haven't been able to give me an answer.
Question up here.
I'm also not an astronomer, so this might be a bit of a side point, but I understood the main point of the talk. So, what is the dusty plane? It sounds like something out of a cowboy film.
These are all made-up names that Rubin made. Let's go all the way back. Okay, so yeah, I didn't want to go into too much detail because that's the galaxy. And so they decided to call it the dusty plane of the galaxy because then some small part of the galaxy, which was argued for reasons, got put into the wide fast deep because some people care about the stars in our galaxy and microlensing and things like that, and so therefore want to observe into the galaxy. Where there's lots of stars, it can be hard to do in terms of processing. Okay for image differencing, where you can look for transients. And so that's mainly when they were arguing about how to do this. They took visits out from the galactic plane and distributed them elsewhere where there wasn't as many stars. So that dusty plane is basically Rubin's definition based on sort of looking at, dust extinction of where, we're getting into the real heart of the Milky Way. And then some small part of it here got put into the wide fast deep because people advocated and went, hold on, we actually do need a little bit in here. And so that part's very much changed from the original sort of version of the survey strategy.
One question up here.
People throw around the worry in big data astronomy of throwing away interesting data, especially when we get so much data. Is this a worry that you think about in this field of LSST? And how do you cope with it, kind of thing?
Great question. I don't worry about it because this data set's going to be worked on for decades. What I worry about is making sure every person who wants to work on this data has access and the ability to get up to speed, because there's so much stuff to learn to get up to speed to understand Rubin Observatory and to get used to the tools and to think on the scale. That's what worries me, is making sure everyone has the opportunity to do that. And it's not like people that have been active for 10 years. I worry about, at night, I worry about, we used to worry about, are we going to lose that part of the northern ecliptic to the cosmologists who totally don't want to look there? How do I argue? So thank you, Planet 9, because we were like, yeah, it's there. Do you want to miss it? It was great. It might not be there, but we still got to look. How do you argue that? I think with any big, step change, there's going to be stuff you miss. But it's going to be there in the data. And so, we should be building the techniques to try to look for that, and that's what some of these outlier algorithms are for, to find the rare gems. But that's the beauty, is that that means that the next generation will be able to go and find it. I just want to make sure we're getting the best data so that we can do that. And so I think through all the work people have done to look at the survey cadence, we have eked out everything we can get for solar system, basically. There's nothing left that I'm worried about. And I'm the pessimist, so I've been telling people last month, I was I'm now an optimist. This is the step change, right? I'm not worried. When I'm not worried, everybody should be celebrating. That the hard work's been done, and so now we get to, there'll be new hard work, we're not going to sleep, but I think that means, you'll be able to go find those things in the data set with some other technique we didn't think of, but it will be there in the data. And the nice thing about solar system objects are they're still there. Well, most of them. Some will decay, break up or whatever, but most of them will still be there. And so you can go hunt if it's really rare and interesting. You can start trying to hunt for it in other observations, things like that. So maybe less worry to say someone who's looking for these rare supernovae or other astrophysical transients because you can't follow it up. That asteroid will be there. It was sitting there. It's been sitting there for a while and been unseen in other surveys, right? So yeah, I think it's develop all the algorithms and let's attack this thing for decades, right? And so this data set's going to be dived into for decades, as other data sets already have shown, smaller surveys, some digital sized survey, which was the greatest at its time, right? So these things are going to be this data set's going to be so rich that the grad students who are not even born yet, right, that are going to be diving at some point using this data in some way.
Oh, yeah.
Thank you for the talk. I just have a question about type of objects, which we will be exploring lots of. So, I think it's very interesting in the sense that you see all these very special orange objects that are out in the full system that are called Pluto and Eris, and even trans-Neptunian objects like Saturn, which is very round. I'm just wondering what would Rubin be able to tell us about how these sort of dwarf planets could form, and what are the ideas that are currently in place for these very special objects?
It's not going to tell us much because we kind of know how they formed. You can take basically models of moving planets, small growing planetesimals, and collide them into each other, and you can build oligarchs that look like Pluto. So we kind of know how to get there. What we don't fully know is how many were in the original disk that got scattered. And so we're going to learn more about that, and then therefore how many of those objects are there, by being sort of learning more about the details of Neptune's migration. So we think there was about 100 Plutos in the planetary disk before Neptune migrated through it. There will be 1 or 2 more dwarf planets found. The really horrible thing is, and I know this because I found a dwarf planet and we know almost nothing about it, is that it's so faint that I can't use spectrographs on the ground. JWST opens the window because there's a lot more we're seeing in the infrared, so that helps. But a lot of the dwarf planets, we don't get much information if they're very distant. So we'll find a few more that'll help us with the size distribution, but we don't necessarily learn much more about the current ones we have. So that's the frustrating bit, is that if you like dwarf planets, this doesn't help you. You want to go use JWST. But again, the further ones that are out, it's going to be harder to use JWST because we're getting less reflected light back. And so that R to the 4, because the light has to go all the way out and all the way back, hurts at the Kuiper belt. That's why it was only really discovered in the 90s. So dwarf planets we'll know a little less about, but we're going to inform about their general formation, the conditions, by looking at everybody else.
Potentially one last question.
Thank you very much for the very interesting talk. I had a question relating to kind of the next generation apparatuses and telescopes. So JWST was clearly a step change, and this is also clearly a step change. But are there any other next generation telescopes you can envision that people are probably designing now that will give you this equivalent kind of capability, or what would you want them to be? Is it just the North Sky, or is it a completely different paradigm of telescope?
I have no idea. For me, it's very weird because I've been co-chair of the Solar System Science Collaboration for almost 9 years. And so my job has been making sure that we get to this point and things start turning online, people are ready. That I honestly haven't thought of what happens after. That I was sitting trying to think about proposal ideas to follow up discoveries, and I was I don't know what to do. So I haven't thought much about what we do next. I think what's exciting is still kind of in the follow-up regime, which is that go in a bigger follow-up telescope. So the ELT is one, because that's good, 30-meter telescope, right, looking at any of these objects, we're now getting some spectra and things about deep into composition we couldn't get. So I think for me, that's where I'm excited. The only problem is that when those things turn on, like JWST, they're 8 to 10 times oversubscribed on time. So you're the hope of getting a proposal through is quite small. It's going to be a while before maybe we see the full impact, as probably commiserations to every of the astronomers in the room that applied for JWST time and did not get it. That there's so many good ideas and great ideas and not enough time because it's so groundbreaking. Rubin's cool in the other way is that because it's just doing its thing, we all get at the same time using basically one cadence. So I would say it's going to be that step change in sort of the follow-up telescopes. The US is trying to build a 30-meter telescope, right? And that there's also the ELT, which is the extremely large telescope. Gotta love the ESO names for things. Got the very large telescope and the extremely large telescope to differentiate them. And so that going from 8-meter to 30-meter, right, that getting your light bucket bigger means all the stuff that was really faint that you can't do, like your dwarf planet spectra, that are very distant, now start becoming things you might be able to do. So that's the thing I can think of off the top of my head. But otherwise, I've basically been how do we get people ready? What's wrong with the cadence? What do we need to do as a community to advocate? And then how do we figure out how much stuff is coming in? So that's been mostly my time. But now it's time to switch gears and start thinking about that question. What do we do next?
Okay. And I think on that note, inadvertently put it on mute. And on that point, looking to the future and thinking about the potential of existing and future instrumentation, and how the youth in the room may be using that in 30 or 40 years' time to inspire the next generation for new observations. Let's thank Megan again for a fascinating. I'd also like to acknowledge the sponsorship of the Royal Astronomical Society, made this lecture series possible. If anyone in the audience is interested in joining the Royal Astronomical Society, come and see me afterwards. I look forward to seeing all of the intrigue and new observations that are going to come in the next decade with the Vera Rubin Observatory. Thank you, Megan.